To calculate precise FET temperatures from a subsystem analysis, we need to extract the boundary conditions at the bottom of a MMIC and use them in a thermal analysis that includes all the FET fine details. Now let's take a look at the LRU thermal analysis we previously calculated. Suppose we're interested in the performance of one of the power amps in one of the TR modules, this one for example. We can extract the conditions at its attachment to the module by going to the Solve menu, Boundary Conditions, and selecting Extract at Exports. Now what this is going to do is go through and find the boundary conditions at every exported device that's included anywhere in the hierarchy of layouts in this LRU. I'll give it a file name for the report so that it can save it. And here's the result. So it's given a number to every exported device, and the power amp we're interested in has been given the designation layout number 10. So we'll scroll down to layout number 10, and we see that it is in fact a power amp that was exported and placed in a TR module, which was exported and placed in the LRU. It's at this location, and then it gives us some statistics about the heat flux through the bottom of the power amp. It gives us the average flux. It gives us the average temperature and the range of temperatures from around 345 degrees Kelvin up to about 359 degrees Kelvin. And then it gives us an approximate film boundary condition that would generate the same average flux. So this is a backside heat transfer coefficient and temperature that could be applied in the power amp simulation to get the same average flux. But the thing we're interested in is producing a more accurate temperature profile on the bottom of the device by using these temperatures that were saved in this boundary condition temperature file. And we can get a closer look at those by slicing the solution at the bottom of the power amps. And then flipping this over and zooming in here to the power amp we're interested in. So if I take the temperature scale and I squeeze it down to this range for the bottom of the device, say from around 340 to 360 degrees Kelvin, I can see the details of the temperature distribution at the bottom of the device. And that's what got saved to the boundary condition file, and that's what we want to apply to the power amp simulation so that we reproduce the same temperature profile. So I'm going to open up another SYMMIC window here and open our power amp MMIC, and I'm going to apply that temperature profile as the boundary condition on the bottom of the device. So I'm going to go Solve, Boundary Conditions, Use Temperature Profile, and go in and select that boundary condition for layout number 10 from the LRU analysis. And then I would just say Run Simulation. I've already done that, so I can just load in the solution. And this is the complete solution of this power amp MMIC using the boundary condition that was calculated from the LRU. This took about 2 to 3 hours to run on my computer. So we don't want to wait for the whole thing to run. We're just going to load in the solution and look at the result. So here's our solution. We can pull up the temperature scale, and if we flip this over and change our temperature scale again to look at the range of temperatures that we expect to be on the bottom of the device from 340 to 360 degrees Kelvin, and I'll just shift this over, and what we can see is that basically we reproduced the profile that we expected from the LRU simulation in the power amp simulation. But in the LRU simulation, the peak temperature over the whole LRU was only 527 degrees Kelvin, whereas now that we apply this higher boundary condition to the bottom of the power amp, we see that the peak temperature in the FETs of the power amp actually reaches 590 degrees Kelvin.